Ekpyrotic universe. Imagine you are folding laundry on a lazy Sunday afternoon. You grab a large bedsheet with both hands, spread your arms wide, and give it a good hard snap to shake out the wrinkles. Whap! That sudden crack of sound and burst of air feels pretty satisfying, right? But what if I told you that something very similar to shaking out that bedsheet might be the reason everything exists? I am talking about you, the Earth, the stars, and every single atom in the vast cosmos. This is the entryway into one of the most mind-bending ideas in modern physics. When we think about the start of the universe, almost everyone pictures the same thing. The Big Bang. We imagine a massive explosion happening out of absolutely nowhere, kicking off space and time in an instant. It is the ultimate origin story, but it leaves us with a nagging question that makes our brains hurt. What happened before the Big Bang? If you ask most traditional physicists, they will tell you that question does not even make sense because time did not exist yet. It is like asking what is located north of the North Pole. Most of us just accept this because it is too hard to wrap our heads around the idea of absolute nothingness suddenly becoming somethingness. But some very clever physicists have come up with a fascinating alternative called the Ekpyrotic universe theory. The word sounds complicated coming from ancient Greek, meaning out of fire, but the idea is actually surprisingly simple if you use your imagination. Forget the singular explosion from nothing. Instead, picture our whole three-dimensional universe as a giant, incredibly thin membrane, or a brain for short. Now imagine this membrane is hanging on a cosmic clothesline right next to another membrane just like it. They are floating very close together in a hidden higher dimension that we cannot see or touch. The Ekpyrotic theory suggests that what we call the Big Bang was simply the moment these two giant cosmic sheets bumped into each other. This changes absolutely everything about how we view our place in reality. If this theory is true, the universe did not just magically appear once. It means cosmic history is a giant, endless loop. Think of two enormous cymbals in an orchestra crashing together. Clang! That crash creates immense heat and energy, filling our membrane with all the stuff that makes up galaxies today. After the crash, the membranes bounce off each other and slowly drift apart. As they separate, our universe cools down and expands, which is the phase we are living in right now. Over billions and billions of years, the universe becomes cold and empty again. But the story does not end there. Eventually, gravity between these two membranes pulls them back together. They speed up, get closer, and wham, they collide, again triggering a brand new Big Bang and starting the whole cycle over. This idea is so profound because it takes away the mysterious singular beginning and replaces it with an eternal cosmic heartbeat. Instead of a one-time firework show that fades into darkness forever, our universe becomes just one breath in an infinite series of breaths. It means that before our universe began, there might have been another one, perhaps filled with its own stars, and maybe even civilizations that lived out their entire history before their universe ended in a fiery collision to give birth to ours. While we do not have definitive proof yet, the Ekpyrotic theory gives us a stunning new way to look at the night sky, wondering if we are just living through one beat in an everlasting rhythm of creation and destruction. The Big Bang theory. Imagine for a moment that you are standing in the middle of a crowded room just after a massive party has ended. Confetti is scattered all over the floor, streamers are draped over the furniture, and there is cake smashed into the carpet. It looks like total chaos. But if you were to watch a video of that party in reverse, you would see something incredible happen. The cake would fly back onto the plate, the streamers would roll themselves up neatly, and every single piece of confetti would float back into the tiny little cannon it came from. Everything that is currently spread out and messy would rush back together into one single, organized point. This is exactly how astronomers and physicists look at our universe. When we look up at the night sky, we see stars and galaxies scattered everywhere. But if we press the rewind button on history, we realize that everything must have started from the same place. Most of us walk around with a very specific image in our heads when we hear the words Big Bang. We usually picture a gigantic explosion happening somewhere in the deep darkness of space, like a stick of dynamite going off in an empty cave. We imagine debris flying out into the void, filling up the empty room that was already there. It is a natural way to think, because that is how explosions work here on Earth. However, this mental image is actually the biggest stumbling block to understanding the true nature of our origins. We tend to think of the universe as a container that holds galaxies, but this view misses the most mind-bending part of the theory. The Big Bang was not an explosion that happened inside of space. It was an explosion of space itself. To understand this, you have to stop thinking about a grenade and start thinking about a loaf of raisin bread dough rising in an oven. Imagine you have a ball of dough filled with raisins. As the dough rises and expands, the raisins move further apart from each other. They are not moving because they have rocket boosters attached to them. They are moving because the dough between them is stretching. In this analogy, the raisins are the galaxies, and the dough is space itself. 13.8 billion years ago, everything we can see today, every star, every planet, and every speck of dust, was squashed together into a single point that was smaller than an atom. This point was infinitely hot and infinitely dense. Then, for reasons we are still trying to figure out, it started to expand outward, stretching space along with it. This concept matters because it completely changes how we view our place in the cosmos. It means that we are not just living in a static, unchanging background. We are living inside an active, evolving event that is still happening right now. The universe is still stretching. The galaxies are still drifting apart. It also connects us to everything else in existence in a very literal way. The atoms in the hand you are using to hold your phone or mouse were once crushed together with the atoms of the most distant stars. We are all pieces of the same initial spark, drifting outward on a wave of expanding space. It turns the universe from a cold, disconnected place into a dynamic story that we are all a part of. The evidence for this theory comes from one of the most famous and accidental discoveries in the history of science. In the year 1964, two radio astronomers named Arno Penzias and Robert Wilson were working at Bell Labs in New Jersey. They were trying to use a massive radio antenna to communicate with satellites, but they kept running into a frustrating problem. No matter where they pointed their antenna, they picked up a low, steady, hissing noise. It was a constant background static that just would not go away. They tried everything to fix it. They checked the wiring, they tightened the connections, they even climbed inside the giant horn-shaped antenna and scrubbed off all the pigeon droppings, thinking the birds were causing the interference. They caught the pigeons and sent them away. But the hissing sound remained. They eventually realized that the noise was coming from everywhere in the sky, day and night. They were not listening to pigeons or broken wires. They were listening to the ancient afterglow of the Big Bang itself. That static was the leftover heat from the birth of the universe, which had cooled down and stretched out over billions of years into microwave radiation. They had accidentally found the cosmic fossil that proved the universe started in a hot, dense state. So the next time you turn on an old television and see that black and white static dancing on the screen, remember that a small percentage of that static is actually the oldest light in the universe, waving at you from the beginning of time. The Big Crunch Theory. Imagine for a moment that you were trying to fit a massive, fluffy sleeping bag back into that tiny little sack it came in. You know the struggle. You push, you shove, and you sweat, trying to compress this giant, chaotic mess into a small, organized space. It feels like a battle against physics itself. Or think about watching a firework explode in the sky. It bursts outward in a beautiful, expanding sphere of light. Now, imagine if you had a remote control for reality and you pressed the rewind button. The sparks would stop moving outward, freeze for a split second, and then rush back together into a single, tiny point before disappearing completely. That feeling of things rushing back together, of compression and returning to the start, is the perfect way to visualize one of the most fascinating ideas in cosmology. This is the story of the Big Crunch. Most of us go through life thinking of the universe as this endless, open stage. We tend to believe that space is just there, getting bigger and bigger, or simply staying the same forever. It is comforting to think that the universe is infinite and that the stars will always be there to wish upon. We rarely stop to consider that the universe itself might have a lifespan, a beginning, a middle, and an absolute end. We assume that because the universe is expanding right now, it will just keep doing that until everything fades away into a cold and dark nothingness. But what if gravity has other plans? What if the universe is not a one-way street, but actually a loop? This is where people often get tripped up, assuming that time only marches forward into emptiness, forgetting that nature loves cycles. The Big Crunch theory proposes a dramatic and fiery end to our cosmos. To understand it, you have to understand the Big Bang. We know the universe started as a tiny, hot, dense point that exploded outward. Right now, galaxies are flying apart from each other because of that initial explosion. However, the Big Crunch suggests that this expansion will not last forever. Think of it like throwing a baseball straight up into the air. The ball travels upward fast at first, but gravity is constantly pulling on it, slowing it down. Eventually the ball stops rising, hangs in the air for a moment, and then comes crashing back down to your hand. In this theory, the gravity of all the stars, planets, black holes, and dark matter acts like the gravity pulling on that baseball. If there is enough stuff in the universe, enough mass to create enough gravity, it will eventually overpower the force of the expansion. The universe will stop growing, pause, and then start to shrink. This concept matters because it completely changes how we view our existence. It turns the universe from a lonely, one-time event into a potential heartbeat. If the Big Crunch happens, everything we see, every galaxy located millions of light-years away, will start rushing toward us. The temperature of the universe would rise drastically. It would not be a cold end, but a spectacularly hot one. As space gets smaller, all the radiation and light created since the beginning of time would be compressed. The universe would become like a giant oven, cooking everything inside it. This matters because it leads to the idea of a cyclic universe. If everything crunches back down into a singularity, that tiny point might just explode again in a new Big Bang, creating a whole new universe with new laws of physics, new stars, and maybe even new versions of us. It implies that perhaps our universe is just one breath in an eternal cycle of expanding and contracting. To visualize this better, we can look at the work of early 20th century astronomers. When Edwin Hubble discovered that the universe was expanding, it shocked the world. But immediately, physicists like Alexander Friedmann began to ask the next logical question, which was simply, will it stop? They realized that the fate of the universe depends entirely on density. It is a cosmic tug-of-war. On one side, you have the momentum from the Big Bang pushing everything apart. On the other side, you have the gravity of all matter trying to pull everything back together. It is exactly like a rubber band being stretched. If you pull it too hard, it snaps and flies apart forever. But if the tension is just right, it snaps back to your thumb. While modern science suggests the expansion is currently speeding up, the Big Crunch remains a powerful reminder of the force of gravity. It teaches us that in the grand scheme of things, what goes up might actually have to come down, collapsing all of history back into the moment of creation. The heat death of the universe. Imagine you have just spent an entire Sunday afternoon deep cleaning your bedroom. You have folded every shirt, organized your desk, and put every single book back on the shelf in perfect alphabetical order. The room looks spotless and pristine. But then, life happens. You get busy with work or school, you rush to find a pair of socks in the morning, and you toss a jacket on the chair. Slowly but surely, without you even trying, the room becomes messy again. You never have to put effort into making your room messy. It just happens on its own. But you have to work very hard to get it back to being clean. Have you ever wondered why that is? Why does it feel like the entire universe is conspiring to ruin your perfectly folded laundry? It turns out that your messy bedroom is actually a tiny example of a massive cosmic rule that will eventually end the universe itself. Most of us go through life thinking that order is the normal state of things, and chaos is just a temporary annoyance that we can fix. We believe that if we just had enough time or energy, we could keep everything perfect forever. We look at a crumbling building, a rusting car, or a fading memory, and think of them as failures or accidents. We assume that things breaking down is something that went wrong. But in the world of physics, breaking down is actually the only thing that is guaranteed to go right. We often struggle to accept that destruction is the natural direction of time. We want to believe that things can last forever, but the laws of physics have a very different plan for us and for everything else in existence. This brings us to one of the most mind-bending concepts in science, which is called entropy and the heat death of the universe. To understand this, you have to realize that heat and energy love to spread out. Imagine pouring a drop of hot red dye into a bowl of cold, clear water. At first, the dye is concentrated in one spot, but over time, it spreads out until the whole bowl is a uniform, lukewarm pink color. Once that happens, the dye never gathers back up into a drop on its own. The universe is acting just like that bowl of water. It started with a massive amount of concentrated energy during the Big Bang. But ever since then, that energy has been spreading out, flowing from hot spots like stars to cold spots like deep space. The theory of the heat death suggests that eventually, all the energy in the universe will be evenly spread out. When that happens, everything will be the exact same temperature. No energy will flow, no stars will shine, no life can exist. It will not be a fiery inferno like the name suggests. Instead, it will be a state of frozen, dark and eternal silence when nothing ever happens again. This concept matters because it defines the very arrow of time. It explains why you can break an egg, but you can never unbreak it. When you crack an egg, you are increasing its disorder, or entropy. To put the egg back together perfectly would require unspreading that energy, which the universe strictly forbids. This law governs everything, from the way our engines burn fuel to the way our bodies age. Every time you eat food, your body takes that concentrated energy and turns it into heat, which radiates away from you. We are all essentially little machines that contribute to the heat death of the universe just by being alive. It sounds a bit gloomy, but it is also what makes this moment right now so special. The fact that we have stars, sunlight, and warm coffee is only possible because the universe has not finished spreading its energy out yet. We are living in the brief, golden era of structure and life before the final equilibrium sets in. To help visualize this, scientists often use the famous example of a deck of cards. Imagine you buy a brand new deck of cards. It comes in a perfect, specific order, which is ace through king for all 4 suits. There is only one way for the deck to be in that perfect order. Now imagine you throw the cards into the air and let them fall to the floor. What are the chances they land in that perfect order again? It is practically 0. There is only one way to be perfectly ordered, but there are billions upon billions of ways to be messy. This is exactly how the universe works. There are infinitely more ways for the universe to be disordered and cold than there are for it to be hot and organized. Over billions of years, purely by the laws of probability, the universe will shuffle itself into a state of total disorder. The stars will burn out, black holes will evaporate, and the cosmos will settle into a permanent state of rest. So the next time you see your coffee getting cold or your room getting messy, remember that you are witnessing the universe slowly drifting toward its ultimate destiny. Cosmic inflation. Imagine for a moment that you are standing in your kitchen holding a small, uninflated party balloon. You take a deep breath and start to blow into it. You expect it to expand slowly, getting a little bigger with every breath you push inside. Now imagine that in less time than it takes to blink your eye, that tiny piece of rubber in your hands suddenly explodes outward. But it does not just get as big as a beach ball. In a fraction of a second, that balloon expands until it is larger than the entire planet Earth, then larger than the Sun, and finally bigger than our entire galaxy. It happens so fast that you do not even have time to be surprised. It sounds like pure magic, or a scene from a superhero movie, right? But according to physicists, this is not magic at all. This is essentially what happened to our universe during its very first moments of existence. When we try to picture the beginning of everything, most of us have a very specific image in our heads. We think of the Big Bang as a standard explosion, like a stick of dynamite going off in an empty room. We imagine stuff flying out into space from a central point, chaotic and messy. We tend to assume that the universe has always played by the rules we see today, expanding at a steady and predictable speed, like a car cruising down the highway. It feels logical to think that if we rewind the clock, the universe would just shrink back down smoothly and slowly. However, nature often defies our logic. If the universe had just expanded slowly and steadily from the start, we would have run into some major problems, The math simply would not add up. The universe would be a lumpy, uneven mess with massive differences in temperature from one side to the other. This brings us to one of the most mind-bending ideas in science, which is called cosmic inflation. Put simply, cosmic inflation is the theory that the universe went through a period of insane, exponential growth right after it was born. We are talking about a time frame so short that it is hard to comprehend. It happened within the first trillionth of a trillionth of a trillionth of a second. During this tiny window, space itself stretched faster than the speed of light. It took a patch of space that was smaller than a single proton and blew it up to the size of a grapefruit almost instantly. It was not matter moving through space. It was space itself creating more space, stretching out the fabric of reality like a giant sheet of rubber being pulled from all directions at once. You might be asking yourself why this matters to you, or why you should care about something that happened 13.8 billion years ago. The answer is surprisingly personal. Without cosmic inflation, you would not be here. If the universe had not stretched out that fast, it would have collapsed back in on itself or become a chaotic soup where stars and galaxies could never form. Inflation smoothed everything out. It took tiny, microscopic jitters in energy and stretched them out across the cosmos. These tiny, stretched-out ripples became the seeds for everything we see today. The denser spots pulled in matter to become galaxies, stars, planets, and eventually, you. The smooth, even temperature of the night sky is a direct result of this sudden growth spurt. To see the proof of this, we can look at a famous map of the oldest light in the universe, known as the cosmic microwave background. When scientists pointed their telescopes at the empty dark space between stars, they found a faint glow coming from every direction. It is like the afterglow of the Big Bang itself. What shocked everyone was that this glow is almost exactly the same temperature everywhere you look, no matter which direction you point the telescope. This would be impossible in a normal explosion, because opposite sides of the universe are too far apart to have ever touched or shared heat. It would be like a cup of coffee in London and a cup of tea in Tokyo, having the exact same temperature down to the decimal point by pure coincidence. Inflation solves this riddle beautifully. It tells us that everything was once touching in a tiny speck, sharing heat, before it was ripped apart instantly. This theory transforms our view of the universe from a simple explosion into a grand, rapid stretching event that set the stage for all of existence. Lambda-CDM Model. Imagine for a moment that you are trying to bake the absolute best chocolate cake for a birthday party. You have gathered all the usual ingredients on the counter. You have the flour, the sugar, the eggs, and the cocoa powder. You mix them all together in a bowl, pour the batter into a pan, and slide it into the oven. You wait patiently, smelling that delicious aroma. But when you finally take the pan out, something is wrong. Instead of a fluffy, tall cake, you have a flat, sad, and runny puddle. You scratch your head and look at the recipe again, only to realize you forgot the two most important things. You forgot the baking powder that makes it rise and the flour that gives it structure. Without those, you do not have a cake. You just have hot, sweet soup. Now, imagine that the entire universe is that cake, and for centuries we thought we knew exactly what was in the recipe. Most of us walk around with a very specific picture of reality. When we look up at the night sky, we see the moon, the planets, and billions of twinkling stars. We naturally assume that what we can see is what exists. It feels logical to think that the universe is made entirely of atoms, the same stuff that makes up your body, your car, the ocean, and the sun. We tend to operate with the mindset that if we cannot see it, touch it, or measure it with a telescope, it probably is not there. We think of the universe as a place filled with visible objects floating in empty space. But physicists discovered that this mindset is actually a massive error. It is like looking at an iceberg and thinking the tiny tip sticking out of the water is the whole mountain, while completely ignoring the gigantic mass hiding underneath the surface. This realization led to the creation of what scientists call the Lambda-CDM Model. It might sound like a complicated name for a robot, but it is actually just the standard recipe for our universe. Think of it as the ultimate cosmic ingredients list. The lambda part stands for dark energy. This is a mysterious force that acts like the baking powder in our cake analogy, pushing the universe to expand faster and faster. The CDM stands for cold dark matter. This is the invisible structure, or the flower, that holds galaxies together so they do not fly apart. The most mind-bending part of this model is what it says about us. The model reveals that everything we have ever seen, every star, every galaxy, and every human being makes up less than 5% of the universe. The Lambda-CDM model tells us that 95% of reality is made of invisible ghosts that we cannot see or touch. You might be wondering why any of this matters to your daily life. After all, you cannot feel dark energy pushing you, and you cannot buy dark matter at the grocery store. But this concept is actually the story of our origins and our destiny. Without the cold dark matter providing extra gravity, the early universe would not have been able to pull gas and dust together to form stars and galaxies. Without it, our solar system would never have formed, and we simply would not exist. On the other hand, the lambda part, or dark energy, is currently winning a cosmic tug-of-war. It is stretching space itself, pushing galaxies away from each other. This means that in the very distant future, the sky will go dark as other galaxies move out of sight. It challenges us to accept that we are not the main characters of the physical world, but rather just a tiny dusting of snow on a massive, invisible mountain. To understand how we know this is true, we have to look at a famous story involving a brilliant astronomer named Vera Rubin in the 1970s. She was studying spiral galaxies, which look like giant spinning pinwheels. Now think about a playground merry-go-round. If you spin it really fast, the children on the outer edge have to hold on tight, or they will fly off. Gravity works the same way. The stars on the edges of galaxies were spinning so fast that according to the laws of physics and the amount of visible matter, they should have been flung out into deep space, but they stayed put. Rubin realized that there simply was not enough visible matter to hold them in. There had to be an enormous amount of invisible mass creating extra gravity to keep the stars from flying away. That invisible mass was dark matter. Her discovery provided the undeniable proof needed for the Lambda-CDM model, showing us once and for all that the universe is far more mysterious and magical than we ever imagined. Einstein's static universe theory. Imagine for a moment that you were trying to build the tallest house of cards in history. You have spent hours carefully placing each card, holding your breath, and making sure your hands do not shake even a little bit. Finally, you place the very last card on top. You step back and look at your masterpiece. It is perfect. It is standing completely still. It is not falling down, and it is not growing taller on its own. It is just frozen there in perfect balance. This desire for balance and stability is something we all crave. We love the idea of things lasting forever, exactly as they are, without changing or falling apart. It feels safe. It feels reliable. When we look at a mountain or the ocean, we want to believe they will always be there, unchanging and eternal. This human desire for permanence extends far beyond just card towers or landscapes. It actually reaches all the way to the stars. For a long time, humanity looked up at the night sky and assumed that what we saw was a fixed backdrop. We thought the universe was like a stage set for a play that never ends. The stars were glued in place, the galaxies were stationary, and the cosmos was just a giant, frozen container that had existed forever and would exist forever. We struggled to imagine something as massive as the universe actually moving, stretching, or changing shape. It feels chaotic and uncomfortable to think that the solid ground of existence might actually be shifting under our feet. This is exactly where Albert Einstein found himself when he was developing his theories of gravity. He proposed a concept known as the static universe theory. When Einstein formulated his general theory of relativity, his equations suggested something troubling to him. They showed that the universe should not be standing still. According to the laws of gravity, all the mass in the universe, every star and every galaxy, attracts every other star and galaxy. This means that if the universe were truly sitting still, gravity should be pulling everything inward. The whole universe should be collapsing in on itself in a giant cosmic crunch. But when Einstein looked out the window, or rather, when he looked at the scientific data available at the time, the universe did not seem to be collapsing. It looked stable. To fix this, Einstein added a special term to his equations. He called it the cosmological constant. Think of the cosmological constant as a magical force that pushes outward to counteract gravity, pulling inward. Imagine you have a deflating balloon that wants to shrink, but you have a machine inside constantly blowing air into it to keep it the exact same size. That is what Einstein did with his math. He invented a repulsive force that pushed against gravity with the exact same strength, keeping the universe perfectly balanced, static, and eternal. He did this not because he had evidence for it, but because he simply liked the idea of a steady and unchanging universe. It felt elegant and right to him. However, the universe does not care about what we find elegant. This theory matters because it shows us that even the smartest person who ever lived can be blinded by their own beliefs. The idea of a static universe delayed our understanding of where we came from. If the universe is static, it has no beginning and no end. But if the universe is not static, if it is moving, that changes everything. This concept is crucial because it was the major roadblock preventing scientists from discovering the Big Bang. By clinging to the idea of a forever universe, we missed the evidence that everything was actually evolving. The illusion of the static universe finally shattered thanks to an astronomer named Edwin Hubble. In the 1920s, Hubble was working at the Mount Wilson Observatory, using the largest telescope in the world at that time. He spent his nights observing distant galaxies. He noticed something that completely contradicted Einstein. The galaxies were not sitting still, and they were not collapsing inward. Instead, they were rushing away from us. In fact, the farther away a galaxy was, the faster it was moving away. This meant the universe was not static at all. It was expanding. It was getting bigger every single second. When Einstein saw Hubble's evidence, he realized his mistake. He had forced his math to fit his preference for a calm and steady cosmos. He later famously referred to the cosmological constant as the biggest blunder of his life. He removed the term from his equations and accepted that we live in a dynamic, expanding universe that started with a big bang. The story serves as a powerful reminder that the universe is far more wild and active than our comfortable desire for stillness would have us believe. We are not living in a frozen house of cards, but rather in the middle of a magnificent, ongoing explosion. Friedmann-Einstein Model. Imagine for a moment that you're standing in the middle of a massive bakery kitchen. You are watching a master baker preparing a special kind of raisin bread. You watch as he places the dough into the oven. Through the glass window, you see something fascinating happen. As the bread rises and expands, the raisins inside the dough start moving further and further apart from each other. But here is the catch. The raisins are not actually swimming through the dough. They are stuck in place. The reason they are getting further apart is that the dough between them is stretching. Now take that image and scale it up. Imagine that you, your house, the Earth, the Sun, and all the distant galaxies are just raisins, and the empty space between us is the dough. This is not just a baking metaphor. This is actually the most accurate way to visualize the universe we live in. It is incredibly difficult for us to wrap our heads around this because we are creatures of habit who crave stability. We walk around every day assuming that the sky above our heads is a fixed, permanent stage. We treat the universe like a rigid cardboard box that does not change size. We assume that space is just an empty container that sits there doing nothing, while stars and planets move around inside it. It feels safe to think that way. We want to believe that the ground beneath our feet and the void above the atmosphere are solid and reliable. We think of the cosmos as a painting on a wall that stays the same yesterday, today, and tomorrow. But physics tells us that this intuition is completely wrong. Space is not a rigid box. It is flexible, it is dynamic, and it is doing something wild right now, while you are just sitting there listening to this. This brings us to one of the most mind-bending concepts in the history of science, known as the Friedmann-Einstein Model. To understand it, we have to look back at Albert Einstein. After he figured out that gravity was actually the curving of space and time, he tried to apply his math to the whole universe. Einstein had a bias, though. He wanted the universe to be eternal and unchanging. But a brilliant Russian mathematician named Alexander Friedmann looked at Einstein's own work and realized the famous physicist had missed something huge. Friedmann saw that the math actually predicted that the universe cannot stand still. He realized that space itself must be either expanding or contracting. He proposed that the fabric of the cosmos is stretching out or crunching in, depending on how much matter is inside it, to hold it all together with gravity. Why does this matter to you and your daily life? Well, it defines the ultimate story of our reality. The Friedmann-Einstein model suggests that the geometry of the universe depends on density. It poses a massive question about our future. If there is enough matter in the universe, gravity might eventually win the tug of war, pulling everything back together until the universe snaps back like a rubber band in a big crunch. If there is not enough matter, space will keep stretching forever until everything is so far apart that the sky goes dark and cold. It changes our perspective from living in a safe, eternal home to living inside a massive explosion that is happening in slow motion. It forces us to realize that stability is an illusion and that change is the only fundamental truth of existence. We are literally riding on a wave of expanding space. The most famous story that illustrates this involves Einstein himself, and it is a great lesson in humility. When Einstein first saw that his equations suggested the universe was moving, he hated the idea. He wanted a static, calm universe so badly that he actually added a fake number, which he called the cosmological constant, to his equations, just to force the universe to stay still mathematically. He essentially cheated on his own homework to get the answer he wanted. But a few years later, an astronomer named Edwin Hubble looked through a telescope and saw that distant galaxies were indeed rushing away from us, just as Friedmann predicted. The raisin bread was rising. Einstein had to admit that forcing the universe to be static was the biggest blunder of his entire career. It serves as a powerful reminder that even the smartest people in history can be blinded by what they want to believe. But eventually, the truth of the universe always reveals itself. Einstein-de Model. Imagine you're standing in an open field holding a baseball. You look up at the sky, wind up your arm, and throw the ball straight up into the air as hard as you possibly can. Now, common sense and basic experience tell you exactly what is going to happen next. The ball will travel upward, slowing down as gravity grabs a hold of it, and eventually it will stop for a tiny fraction of a second before falling right back down to Earth. But imagine if you were strong enough to throw it fast enough to escape Earth entirely. In that case, the ball would zoom away, never to return. But is there a middle ground? Is there a perfect, magical speed where the ball keeps going up forever, getting slower and slower, but never actually stopping and never falling back down? It is a weird concept to grasp, balancing right on the edge of two extremes. This specific kind of balance is something human beings often struggle to visualize. We tend to think in binary terms. We see things as black or white, success or failure, expansion or contraction. When we think about the universe, we usually assume it has two potential destinies. Either it explodes outward forever until it rips apart, or gravity wins the tug of war and everything crashes back together in a fiery crunch. We rarely stop to consider the mathematical elegance of the razor edge that lies right between those two chaotic endings. We overlook the possibility of a universe that is perfectly balanced, calm, and incredibly flat. This tendency to ignore the middle ground is exactly what makes the physics concept we are discussing today so fascinating. This brings us to one of the most elegant and historically important ideas in cosmology, known as the Einstein-de Model. Proposed in 1932 by Albert Einstein and the Dutch mathematician Willem de Sitter. This theory was an attempt to describe the geometry and destiny of our universe in the simplest way possible. At the time, astronomers knew the universe was expanding, but they did not know what the future held. Einstein and de Sitter suggested a universe that contains only matter, no dark energy, no mysterious forces pushing things apart, just good old-fashioned matter and the gravity that comes with it. In this model, the universe has just enough matter that its gravity eventually slows the expansion down to almost zero, but never quite causes a collapse. It is a flat universe. It represents the cosmic version of that baseball flying upward, slowing down forever, but never falling back down. You might be wondering why a model from the 1930s matters to you today, especially since we now know the universe is a bit more complicated. The reason this concept is so crucial is that it represents the baseline for reality. It is the perfect recipe. If the universe had started with slightly more matter, gravity would have been too strong. Everything would have crunched back together before stars, galaxies, or life could ever form. If there had been slightly less matter, the universe would have expanded so fast that atoms would never have found each other to build the Earth you are standing on. The Einstein-de Model describes a universe that is finely tuned for existence. It highlights the precarious balance required for us to be here. It reminds us that our existence rests on a knife edge between a violent crunch and a frozen void. To see why this model held the crown for so long, we have to look at the scientific narrative of the 20th century. For decades, the Einstein-de Model was considered the standard for how our universe worked. It was elegant, simple, and relied only on matter and gravity. Physicists loved it because it was mathematically beautiful. But nature had a surprise in store. In the late 1990s, two teams of astronomers decided to measure how much the universe was slowing down, fully expecting to confirm the Einstein-de Model. They observed distant exploding stars called supernovae. What they found shocked the world. The universe was not slowing down, as Einstein and de Sitter predicted. It was speeding up. They discovered dark energy. While the Einstein-de Model turned out to not be the final description of our specific universe, it remains the most important educational tool in cosmology. It is the perfect, simple standard that helps us understand just how strange and complex our actual reality truly is. Cyclic theories, or cyclic model. Have you ever had one of those days where you feel like you are completely stuck in a time loop? You know exactly the feeling I am talking about. You wake up to the same alarm, drag yourself out of the same bed, drink the exact same coffee, sit in the same traffic, and do the same work you did yesterday. It feels endless. We humans actually find a lot of comfort in cycles. The sun rises and sets every single day without fail. The seasons change from summer to fall to winter and back to spring. It is the steady rhythm of life that keeps us grounded. But have you ever stopped to wonder if the entire universe plays by these same rules? What if the cosmos is not just a one-time show, but actually an infinite series of reruns? Most of us grow up believing in a very specific story about how everything began. We are told that once upon a time, about 14 billion years ago, there was a Big Bang. According to this standard view, everything we know, from the massive stars burning in the sky to the tiny atoms in your fingertips, just exploded into existence out of nowhere. It is a linear story. It has a clear beginning, a middle, which is right now, and eventually a lonely end, where the stars burn out, and everything fades to black. We tend to think of history as a straight line moving forward. It is intuitive to think that way because we are born, we live, and eventually we pass away. We assume the universe must have a birthday and a death day too. But asking what happened before the Big Bang usually leads to a frustrating answer. Scientists often say that question makes no sense, similar to asking what is north of the North Pole. But some physicists have a wilder idea that challenges everything we think we know about time and creation. This is called the cyclic model. Imagine for a moment that the Big Bang was not actually the beginning of everything. Instead, picture it as a bridge or a transition between eras. In this view, the universe is like a giant cosmic lung. It breathes out, expanding and growing for billions of years, and then it potentially slows down. In some versions of this theory, it breathes back in, crunching back down into a tiny point, only to bounce back out again in a new Big Bang. According to this theory, the universe does not have a birthday, and it will never have a funeral. It has simply always been here, undergoing an endless cycle of death and rebirth. Now you might be wondering why this actually matters to us down here on Earth. It matters because it solves the biggest headache in cosmology. If the universe has always existed in a cycle, we no longer need to worry about how something came from nothing. It changes our perspective from viewing our existence as a lucky accident on a straight line to seeing ourselves as part of an eternal rhythm. It suggests that the conditions for life might happen over and over again throughout eternity. It changes the universe from a one-way street into a grand, infinite loop. It makes the cosmos feel less like a fleeting spark in the dark and more like an eternal machine that never stops working. To help you visualize this, think about two parallel bed sheets hanging on a clothesline, blowing gently in the wind. These sheets represent different dimensions of reality. Most of the time, they just float near each other. But every few trillion years, gravity pulls them together and they smash into one another. That collision releases a massive amount of energy. To an observer inside the sheet, that smash looks exactly like a hot, fiery Big Bang. This is actually based on a real scientific proposal called the Ekpyrotic universe. It suggests that our universe was created from the collision of two other worlds. Once the energy settles, the sheets drift apart, the universe cools and expands, only for them to eventually crash into each other again down the road. It is a story where the end of the old world is just the spark that lights the fire for a brand new one. Oscillatory universe theory. Imagine for a moment that you are building a massive, intricate house of cards. You spend hours placing every card with perfect precision. It is delicate and beautiful. But eventually, gravity wins, or perhaps a breeze blows through the window, and the whole thing comes crashing down. It is a moment of chaos and destruction. But then, instead of walking away, you sweep up the cards, shuffle the deck, and immediately start building again. You do this over and over, forever. Now imagine that house of cards is not just a stack of paper, but the entire universe, including every star, every galaxy, and even you. This is the essence of one of the most fascinating ideas in cosmology. Most of us live our lives with a very specific mindset about time. We view everything as a straight line. We are born, we grow up, we grow old, and eventually our time ends. We apply this same logic to history and to the universe itself. We are taught that about 13.8 billion years ago, there was a Big Bang. The universe exploded out of nothingness. It has been expanding ever since, and one day, trillions of years from now, it will likely freeze over and fade into eternal darkness. It is a one-way trip from a bright beginning to a lonely end. This linear way of thinking can make human existence feel incredibly small and fleeting, like a brief spark in an infinite night. But there is a theory that challenges this one-way ticket scenario completely. It is called the Oscillatory universe theory, or sometimes the Cyclic model. The core idea is incredibly simple, but deeply profound. It suggests that the Big Bang was not the beginning of time, but merely the start of a new phase. According to this theory, the universe is like a gigantic cosmic lung. Right now, we are in the inhalation phase. The universe is expanding, stretching out and growing, but eventually this expansion might run out of energy. Gravity, the force that pulls everything together, could take over. The universe would stop expanding and begin to contract. Galaxies would be pulled back toward each other, getting closer and hotter and denser, until everything crashes back together into a single, infinitely hot point. Scientists call this the Big Crunch. But here is the twist. Instead of ending there, that pressure triggers a massive rebound, a big bounce, launching a brand new Big Bang and starting the cycle all over again. This concept changes everything about how we see reality. It implies that time does not have a beginning or an end. Instead, reality is an infinite loop of death and rebirth. It mirrors the cycles we see in nature right here on Earth. Think about the seasons. Winter brings a kind of death to the landscape, but it is always followed by spring. Think about the water cycle, where rain falls, evaporates, and forms clouds to rain again. If the oscillatory universe theory is true, then the cosmos itself is just the ultimate version of this natural rhythm. It suggests that we might be living in just one of an infinite number of universes that have existed before us, and an infinite number that will come after us. It makes the universe feel less like a machine running down and more like a living, breathing entity. This might sound like pure science fiction or ancient philosophy, but serious physicists have championed versions of this idea. One of the most famous examples involves the Nobel Prize-winning physicist Sir Roger Penrose. He proposed a theory called Conformal Cyclic Cosmology. Penrose argued that he found evidence of these past universes hidden in the data we have right now. When we look at the oldest light in the universe, known as the cosmic microwave background, it looks mostly like static. However, Penrose pointed out specific circular patterns in this map of ancient light. He suggested that these rings were actually the gravitational echoes of massive black hole collisions from a previous universe that existed before our Big Bang. He essentially claimed that we can see the ghosts of a universe that died so that ours could be born. While not every scientist agrees with his interpretation, it is a stunning reminder that what we think is the absolute beginning might actually just be the turning of a page in a story that never ends. Fecund universes theory. Have you ever looked at an old family photo album and noticed how your grandfather's nose or your grandmother's smile shows up on your own face? It is kind of spooky how traits get handed down from generation to generation, right? We accept this as a basic fact of life. Biology dictates that living things have babies, and those babies look a bit like their parents, but with tiny little changes. It is just how evolution works here on Earth. We are totally comfortable with the idea that your dog, your houseplant, and you are the result of millions of years of ancestors passing down traits. But here is the thing, where most of us get stuck. When we think about the vast universe out there, with all its swirling galaxies and gigantic stars, we usually think of it as cold-dead and unchanging. We see physics as a rigid set of rules written in stone at the very beginning of time. We rarely stop to imagine that the cosmos itself might act a lot like a living thing. We struggle to wrap our heads around the idea that the universe might actually have a family tree just like you do, and that it might be evolving right now. This brings us to one of the most mind-bending ideas in modern physics. It is called the Fecund universes theory, or sometimes it goes by the name Cosmological natural selection. Physicist Lee Smolin proposed this idea, and it sounds absolutely wild at first glance. In extremely simple terms, the theory suggests that black holes are not just dead ends where matter goes to get crushed into nothingness. Instead, they are actually cosmic nests. The core idea is that every single time a massive star collapses and a black hole forms, it creates a brand new baby universe on the other side, spouting out into its own separate reality that we can never reach. Why does this weird idea even matter to us? Well, it addresses a massive puzzle that keeps physicists up at night, called the fine-tuning problem. Here is the issue. Our universe seems suspiciously perfect for existence. If gravity were just slightly stronger, everything would crush together instantly. If it were slightly weaker, stars would never form. It is like our universe is the ultimate Goldilocks scenario, where everything is just right. If universes just randomly pop into existence, the odds of getting one as perfect as ours are practically zero. It feels like a fix is in. But if Smolin's theory is right, it changes everything, because it applies biology to astronomy. To understand how this solves the puzzle, think back to biological evolution. Animals that are better at surviving have more babies passing on their successful traits. In the Fecund universes theory, a successful universe is not necessarily one that has life in it. A successful universe is one that is really good at making black holes, because black holes mean babies. When a baby universe is born, it inherits the laws of physics from its parent universe, but with tiny random mutations. If those little tweaks make it better at producing giant stars that collapse into black holes, that baby will eventually have tons of its own offspring. Over billions of cosmic generations, you end up with a multiverse dominated by universes that are finely tuned machines for creating black holes. And guess what? The exact conditions needed to make lots of black holes just happen to be the almost exact same conditions that allow stars, planets, and eventually people like us to exist. So in this mind-bending view, we might just be an accidental byproduct of a universe trying to be the best parent it can possibly be. Black hole cosmology. Have you ever stared at a snow globe and wondered what it would be like to live inside that tiny, glass-enclosed world? You shake it up, watch the glitter settle, and for the people inside that miniature village, that glass sphere is the edge of their entire existence. They have no idea that they are sitting on a shelf in a much larger room, which is inside a house, which is on a planet, and so on. It sounds like a scene from a science fiction movie. But what if I told you that this might actually be our reality? There is a very real possibility that our entire universe, everything we see and know, is just the inside of a massive cosmic container floating in a much larger space. Most of us walk around assuming that the universe we live in is the main event. We are taught in school that around 14 billion years ago, everything just exploded into existence from a single, incredibly hot point called the Big Bang. We tend to think of this as a unique, one-time miracle that happened out of nowhere. On the flip side, when we look at black holes in space, we usually see them as cosmic monsters that destroy everything they touch. We picture them as dead ends where matter goes to be crushed into nothingness. It is hard for our brains to imagine that these terrifying dark spots might actually be the seeds of creation rather than destruction. We usually assume that a black hole is where the story ends, but physics suggests it might be where a new story begins. This brings us to one of the most mind-bending theories in physics called black hole cosmology. Put simply, This theory suggests that our universe might actually exist inside a massive black hole belonging to another, much older universe. Instead of the Big Bang being the ultimate beginning of everything everywhere, it might have just been the moment a star collapsed in a parent universe, creating a black hole that expanded on the inside to become our home. It implies that every black hole we see in our own night sky could potentially contain a baby universe of its own, hidden behind a boundary that we can never cross. In this view, our universe is not the only one. It is just one bubble floating in a sea of other bubbles. You might be wondering why this actually matters to you, or why scientists would even spend time thinking about it. Well, it solves a huge mystery that has bothered scientists for decades. Our universe seems almost too perfect. If the force of gravity were slightly stronger or slightly weaker, stars would never form, and we would not be here. It feels like we won a lottery with odds so low they are basically impossible. However, under this theory, universes undergo a sort of cosmic natural selection. Universes that are good at making black holes reproduce and create more universes. Since black holes are formed by dying stars, a universe needs to be good at making stars to survive. We live in a universe full of stars and life because those are the specific conditions needed to create more baby universes. It shifts our perspective from thinking we are a lucky accident to realizing we might be part of a grand, evolving cosmic family tree. To help visualize this, the theoretical physicist Lee Smolin proposed an idea that works a lot like Russian nesting dolls. You know those wooden dolls where you open one up and find a smaller one inside, and then another inside that one. Smolin suggests that our reality is exactly like that, but on a scale we can barely comprehend. In his view, the laws of physics are not set in stone, but are inherited from our parent universe, just like you inherited traits from your parents. Every time a black hole forms, it tweaks those laws slightly. This means that right now, somewhere in the center of a distant galaxy, a black hole might be birthing a new reality with totally different rules of physics. It paints a picture of a multiverse that is not just a random collection of bubbles, but a living, breathing ecosystem where our universe is just one link in an infinite chain of creation. White hole theory. Imagine you are holding a porcelain mug filled with hot coffee. Suddenly, it slips from your fingers. It crashes onto the kitchen floor, shattering into 100 sharp pieces while the brown liquid splashes everywhere. In that moment of regret, you probably wish for a superpower. You wish you could hit a cosmic rewind button. You want to see the coffee lift itself off the floor and dive back into the cup. You want the ceramic shards to fly together and seal themselves up until the mug is sitting perfectly whole in your hand again. It feels impossible. We are used to things breaking, falling, and ending. We are definitely not accustomed to things unbreaking, rising, and beginning backward. The arrow of time seems to only point one way, marching us relentlessly forward into a future that is often messier than the past. This feeling that the universe is a one-way street is how most of us navigate our lives. We pour milk into tea, and it mixes, but it never separates back out on its own. We get older, never younger. We tend to think of the cosmos as a place where energy eventually runs out and things get sucked into oblivion. When we think of space, we usually obsess over the ultimate monsters of destruction known as black holes. We picture them as these giant cosmic vacuum cleaners that eat everything, including light, never letting anything escape. It is a scary thought that the universe is just full of heavy traps waiting to crush matter into nothingness. We accept that gravity is a force that pulls things in, captures them, and locks them away forever. But what if the very same mathematics that predicts those monsters also predicts their complete opposite? Enter the mind-bending concept of the white hole. If a black hole is a trash compactor where you check in but never check out. A white hole is the exclusive exit door where nothing can enter, but everything comes rushing out. Imagine a region of space that is pure, endless creation. It is like a cosmic fountain spewing out matter and light. In the simplest terms, a white hole is just a black hole running in reverse. If you filmed a black hole eating a star and then played that movie backward, what you would see is a white hole. It pushes things away with the same intensity that a black hole pulls them in. It is a region of space-time that is mathematically possible, yet we have never officially seen one, making it the ghost story of the physics world. Why does this matter to anyone not piloting a spaceship? Because it helps solve a massive headache for physicists regarding where stuff goes when it supposedly dies. There is a fundamental rule in physics that says information cannot be destroyed. If a black hole eats a library, the information in those books has to go somewhere. White holes suggest a back door to the universe. Maybe what falls into a black hole in one place gets spit out by a white hole in another place, or even another time. This changes our entire view of reality, from a story about destruction to a story about recycling. It even hints that our very existence, the Big Bang itself, might have been just one giant white hole exploding everything into existence. It suggests that the universe breathes in and breathes out, and nothing is ever truly lost, only transformed and relocated. To visualize this, let us look at the work of the famous theoretical physicist Carlo Rovelli. He uses a brilliant analogy involving a simple ball. Imagine you hold a ball high up and drop it. It falls faster and faster, guided by gravity, just like matter falling into a black hole. But what happens when the ball hits the ground? It does not vanish. It compresses for a tiny fraction of a second, stops, and then bounces back upward. Rovelli suggests that a black hole eventually reaches a point where it cannot get any smaller or heavier. At that moment, quantum mechanics takes over, and it rebounds. The black hole transforms into a white hole. The star that died and collapsed essentially bounces back out. This means the terrifying end of a star is actually just a pause before a new beginning. It turns the darkest objects in the universe into bright beacons of creation, proving that even in the deepest void, there is always the potential for a return. Conformal cyclic cosmology. Imagine for a moment that you were sitting in a movie theater. The screen goes dark, the credits roll, and the lights come on. You stand up, stretch your legs, and walk towards the exit, knowing that the story is finished. This is how we intuitively understand the world. Everything has a start, and everything has a finish. You are born, you live, and you die. A song begins, it plays, and it ends in silence. It feels natural to think that existence works the same way. We embrace the idea that our universe had a singular birthday, and that one day, far in the future, it will have a permanent funeral. But what if the movie theater never actually closes? What if, just as the credits finish, the screen flickers, the music swells, and an entirely new movie begins immediately, born from the ashes of the last one? This is the unsettling and beautiful question posed by one of the most mind-bending theories in modern physics. Most people navigate life assuming that history is a straight line. We look at the history of the cosmos and see a timeline that starts at point A and moves toward point B. We are taught that the Big Bang was the ultimate beginning of everything. Before that moment, we are told, there was nothing. Not just empty space, but literally nothing. Physics teachers often say that asking what happened before the Big Bang is like asking what is north of the North Pole. It is considered a nonsense question because time itself did not exist yet. This mindset leaves us with a somewhat bleak picture of the future. We believe the universe is expanding and cooling down, and eventually it will undergo a heat death. This means all the stars will burn out, galaxies will drift apart, and the cosmos will become a frozen, dark and lonely wasteland forever. It is a depressing thought that eventually nothing we do will matter, because the stage we stand on will simply dissolve into darkness. However, the Nobel Prize-winning physicist Sir Roger Penrose suggests we have been looking at this timeline all wrong. He proposes an idea called Conformal Cyclic Cosmology. While the name sounds intimidating, the concept is surprisingly elegant. Penrose argues that our Big Bang was not the beginning of everything. Instead, it was merely the transition point between an old, dying universe and our new, young one. In his view, the universe goes through infinite cycles called eons. Just like the seasons change from winter to spring, the death of one universe naturally creates the conditions for the birth of the next. It suggests that our universe is just one chapter in an endless book that has no front cover and no back cover. To understand how a dead, cold universe can suddenly turn into a hot, fiery Big Bang, we have to look at how we measure things. Right now, the universe is full of stuff like planets, stars, and people. All of this stuff has mass, and mass acts like a clock. It gives us a sense of scale and time. But billions of years from now, all the stars will die, and even the black holes will eventually evaporate away. The universe will be left with nothing but light particles or photons. Here is the fascinating part. Light does not experience time, and it does not have mass. When the universe is empty and contains only light, it literally forgets how big it is. In the eyes of physics, an infinitely large, cold and empty universe looks mathematically identical to an infinitely small, hot and dense point. Because the universe loses track of its own size, the end of the vast, cold cosmos becomes the seed for a new, hot Big Bang. This might sound like pure philosophy, but Penrose claims there is actual evidence for this cycle imprinted on the sky. He suggests that we can see the ghosts of the universe that came before ours. When massive black holes collided in the previous eon, they sent out powerful gravitational waves. Penrose believes these waves were so strong that they survived the transition into our universe. He points to strange rings found in the cosmic microwave background, which is the radiation left over from our Big Bang. He calls these Hawking points. Think of them like ripples in a pond that remain even after the stone has sunk to the bottom. If he is right, those rings are the echoes of a dead universe, proving that we are living amidst the wreckage and the rebirth of an eternity that never truly ends. Quintessence. Imagine you are driving your car up a steep hill. You take your foot off the gas pedal to let the car coast. Naturally, you expect the car to slow down because gravity is pulling it back and friction is working against the tires. This is how the world works. This is how our intuition works. Things that are pushed eventually slow down when the pushing stops. Now imagine that instead of slowing down, your car suddenly starts speeding up all on its own. You are not touching the gas, yet you are accelerating faster and faster towards the top of the hill. It would feel like a ghostly hand is pushing you from behind, harder and harder with every passing second. This scenario sounds like a scene from a science fiction movie or a dream. But in the vast and mysterious world of cosmology, this is exactly what is happening to our universe right now. Most of us go through life thinking that the universe is a stable and predictable place. We tend to believe that what goes up must come down. For the longest time, even the smartest scientists believed that the expansion of the universe, which started with the Big Bang, would eventually slow down. The logic was simple and sound. The universe is full of massive objects like stars and galaxies, and all of these objects have gravity. Gravity is an attractive force, meaning it pulls things together. Therefore, all the gravity in the universe should be acting like a giant brake, pulling everything back together and slowing down the expansion. It is a comforting thought because it implies a certain order and balance. We like to think that forces balance out and that we understand the rules of the game. But nature has a funny way of breaking the rules we think we know. This is where we introduce the mind-bending concept known as quintessence. To understand quintessence, we first have to talk about dark energy. Dark energy is the mysterious force that is pushing the universe apart, acting in opposition to gravity. For a long time, physicists thought dark energy was just a constant, unchanging force, something they call the cosmological constant. Think of the cosmological constant like a cruise control setting in a car that is locked at 60 miles per hour. It never changes. But quintessence suggests something far more dynamic and strange. The theory of quintessence proposes that dark energy is not a static background number, but rather a dynamic, changing field that evolves over time. The word itself comes from the ancient Greeks, who believed the universe was made of earth, air, fire, and water, plus a fifth element called quintessence, which made up the stars and heavens. In modern physics, it represents a fifth fundamental force. If the cosmological constant is a cruise control locked at one speed, quintessence is like a driver who can decide to press the gas pedal harder or ease off a little bit depending on the road conditions. Understanding this concept matters because it completely changes the destiny of our universe. If dark energy is just a constant static force, we can pretty much predict how the universe will end. It will just keep expanding forever until everything is cold and dark. But if quintessence is real, the story becomes a lot more of a thriller with multiple possible endings. Because quintessence can change over time, it means the strength of the push expanding the universe could change. It could get stronger, or it could get weaker. If it gets stronger, it could lead to something called the Big Rip, where the expansion becomes so violent that it tears apart galaxies, then solar systems, then planets, and finally atoms themselves. Everything would be shredded. On the other hand, if quintessence weakens and eventually flips, it could stop the expansion entirely and let gravity win. This would cause the universe to collapse back in on itself in a big crunch. This theory matters because it tells us that the future is not written in stone. It adds a layer of complexity and unpredictability to the cosmos that challenges our desire for simple answers. To really grasp how shocking this realization was, We have to look back at a famous moment in science history from the late 1990s. Two independent teams of astronomers, the Supernova Cosmology Project and the High Z Supernova Search Team, were observing distant supernovae. These are exploding stars that act like cosmic lighthouses. By measuring how bright these explosions were, the scientists hoped to measure how much the universe was slowing down. They expected to find that the expansion was decelerating due to gravity. But when they crunched the numbers, they found something impossible. The supernovae were dimmer than they should have been. This meant they were farther away than expected. The universe was not slowing down at all. It was speeding up. This discovery won the Nobel Prize and forced humanity to accept that 70% of the universe is made of a mysterious energy, pushing everything apart. Quintessence is our best attempt to describe that energy, not as a boring, static number, but as a living, breathing field that dictates the flow of cosmic history. It reminds us that even in the cold vacuum of space, the universe is capable of change, evolution, and surprises that we are only just beginning to understand. The Multiverse Theory. Have you ever laid awake at night, staring at the ceiling, and wondering what would have happened if you had just said hello to that cute stranger 3 years ago? Or maybe you stress over small things, like whether you should have ordered the pizza instead of the salad for lunch. We all play the what-if game. It is a universal human experience to look back at the crossroads in our lives and wonder about the path we left behind. We usually treat these unchosen paths as nothing more than fantasies or daydreams that vanish the moment we make a decision. You assume that because you took the job in New York, the version of you that took the job in London simply never existed. We feel that once a choice is made, the door to the other option closes and locks forever. We generally operate under the firm belief that reality is a single straight line. We think that history is a singular series of events where we move from the past into the future, and every decision creates a definitive outcome while destroying all other possibilities. This mindset makes us fear making the wrong choice because we believe we only get one shot at getting it right. We treat our lives like a video game with only one save file. But physicists have a theory that challenges this entire way of thinking. It suggests that reality is not a single line at all, but rather a sprawling and infinite tree of possibilities. This is what is known as the multiverse theory, or more specifically in quantum mechanics, the many worlds interpretation. The core idea here is deceptively simple, yet absolutely mind-blowing. The theory proposes that every time a quantum event has more than one possible outcome, all of them actually happen. Nature does not choose one option and discard the rest. Instead, reality splits to accommodate every single possibility. If you have a choice between wearing a red shirt or a blue shirt, you do not actually choose one. You choose both. In one branch of reality, you put on the red shirt and go about your day. In another, equally real branch, you put on the blue shirt. These two worlds are distinct and separate, but they are both completely real. This means that every regret you have ever had is actually a reality for a different version of you. This concept completely changes how we view our place in the universe. It suggests that there are infinite versions of you living out every possible life. There is a universe where you are a famous rock star playing to sold-out stadiums. There is another universe where you invented a new technology that saved the world. There is also likely a universe where you made a terrible mistake that you managed to avoid in this one. It makes the universe feel incredibly crowded, yet strangely lonely, as these infinite versions of ourselves can never communicate with one another. It implies that everything that can happen does happen. This removes the weight of destiny and replaces it with the weight of infinite probability. To understand why scientists actually take this seriously, we have to look at a famous thought experiment devised by the Austrian physicist Erwin Schrödinger in the 1930s. You have likely heard of it. It is called Schrödinger's cat. Imagine you place a cat inside a sealed steel box. Along with the cat, you place a tiny amount of a radioactive substance so small that perhaps one atom decays, or perhaps it does not. If the atom decays, it triggers a mechanism that releases poison and sadly kills the cat. If the atom does not decay, the cat remains alive. According to the rules of quantum mechanics, until you open the box to check, the atom is in a state of being, both decayed and not decayed at the same time. This implies that the cat is both alive and dead simultaneously. In the traditional view, opening the box forces nature to choose one state. The cat becomes definitively alive or definitively dead. But the many worlds interpretation says that nature never chooses. Instead, at the moment of the event, the universe splits in two. In one universe, you open the box and find a live cat. In another universe, you open the box and find a dead cat. Both outcomes are true, and there is a version of you witnessing each one. So the next time you feel paralyzed by a difficult decision, just remember that somewhere out there in the vast multiverse, another version of you has already taken the other path. The simulation theory. Have you ever been playing a video game with graphics that looked incredibly realistic, where the sunlight hit the water just right, and for a split second you forgot you were staring at a screen? You became so absorbed in the mission or the story that the controller in your hand seemed to disappear from your awareness. Now imagine for a moment that the characters in that game suddenly gained consciousness. Imagine they started asking questions about their world. They might wonder why the sky is blue or why they cannot walk through walls. To them, their digital world would feel completely solid and absolute. They would have no idea that they were just lines of code running on a console in someone else's living room. Now, take a deep breath and ask yourself a slightly terrifying question. How do you know that you are the player holding the controller and not the character inside the screen? We go about our daily lives with a very specific kind of confidence. We trust our senses implicitly. When you pick up a cup of coffee, you feel the heat against your palm. When you bite into an apple, you taste the sweetness. When you stomp your foot on the ground, it feels solid and immovable. Because our sensory experience is so vivid and consistent, we naturally assume that this universe is the base level of reality. We assume that what we see is exactly what exists. It almost feels silly to question it. We look at the history of human progress, from stone tools to smartphones, and we view ourselves as biological creatures evolving on a physical planet. The idea that our reality might be artificial feels like something that belongs strictly in science fiction movies, not in serious scientific discussion. However, this is exactly what the simulation theory proposes, and it is taken very seriously by some of the smartest physicists and philosophers in the world. Put simply, the simulation theory is the hypothesis that our known universe, including the Earth, the stars, your body, and even your consciousness, is actually a computer-generated simulation. The idea suggests that a civilization with technology far more advanced than ours, perhaps thousands or millions of years ahead of us, has built a computer powerful enough to simulate an entire universe. In this scenario, what we call the laws of physics are just the programming code that governs the simulation, and we are the artificial intelligence living within it. You might be wondering why this concept actually matters, or why it is anything more than a fun thought experiment. It becomes compelling when you look at how our universe behaves. Physicists have long noticed that the universe follows strict mathematical rules, almost like computer code. For example, think about the speed of light. In our universe, light travels at a specific maximum speed, and nothing can go faster than it. In the world of computing, this looks suspiciously like a hardware limit, similar to how a computer processor has a maximum speed at which it can process information. Furthermore, in video games, to save processing power, the computer only renders the parts of the world that the player is currently looking at. In quantum physics, we have discovered something called the observer effect, where tiny particles do not seem to have a definite position until we actually measure or observe them. It is almost as if the universe is saving memory by only rendering reality when we are watching. This brings us to a famous logical argument presented by the philosopher Nick Bostrom in the year 2003. He proposed a trilemma, which is a problem with three possibilities. He argued that one of three things must be true. First, it is possible that all civilizations go extinct before they become technologically advanced enough to create realistic simulations. Second, perhaps civilizations do reach that level of technology, but they simply lose interest and choose not to run simulations of their ancestors. Or third, civilizations do reach that level, and they run many, many simulations. If the third option is true, then there would be billions of simulated universes and only one real original universe. Statistically speaking, if there are billions of fake worlds and only one real one, the odds that we are in the one single real reality are essentially zero. This logic suggests that it is overwhelmingly likely that everything you know, everyone you love, and every memory you have is a product of a highly advanced hard drive. So the next time something strange happens, like a coincidence that feels too perfect, you might just be witnessing a glitch in the code. Quantum mechanics. Have you ever lost your keys, looked on the kitchen table, and swore they were not there, only to look again 10 seconds later and find them sitting right in plain sight? It feels like a glitch in the matrix, doesn't it? For a split second, you question your own sanity or wonder if reality just decided to play a trick on you. We usually laugh these moments off as just being forgetful or distracted. But what if I told you that at the deepest, most fundamental level of the universe, things actually do behave like that? What if reality is not solid and fixed, but is actually a shimmering, blurry mess of possibilities that only snaps into place when you decide to look at it? Welcome to the strange world of physics, where magic is real and common sense goes out the window. We move through our lives assuming that the world follows strict, predictable rules. If you drop a coffee mug, gravity pulls it down and it smashes on the floor. If you park your car in the driveway, you expect it to stay there all night, unless someone moves it. We find comfort in this certainty. We like to think of the universe as a giant, reliable clockwork machine where one gear turns another, and everything happens for a logical reason. We assume that an object is either here or there, but never both places at once. We assume that the past is done and the future hasn't happened yet. But physicists discovered something terrifying and wonderful about 100 years ago. They found out that while the big things we see every day follow these rules, the tiny building blocks that make up everything, including you and me, do not follow the rules at all. This brings us to the concept of quantum mechanics. Now, please do not let the fancy name scare you away. At its core, quantum mechanics is just the study of how very small things, like atoms and electrons, behave. In our normal world, a tennis ball is just a tennis ball. It has a specific location and a specific speed. But in the quantum world, a particle is not just a hard little marble. Instead, it is more like a fuzzy cloud of probability. Imagine a coin spinning on a table. While it is spinning fast, is it heads or tails? You cannot really say it is one or the other. It is a blur of both heads and tails simultaneously. That is exactly how particles exist. They do not pick a state until they are forced to interaction with something else. They exist in a superposition, meaning they are everything and everywhere all at once until the moment they are measured. You might be thinking that this sounds like abstract philosophy or science fiction that has nothing to do with your real life. But the truth is, this weirdness is the engine that powers the modern world. If these tiny particles acted like normal miniature tennis balls, your smartphone would not exist. The computer or television you are using to watch this right now relies entirely on our ability to manipulate these unpredictable quantum particles. Technologies like lasers, MRI machines in hospitals, and even the nuclear power that lights up millions of homes are all based on the fact that reality is fuzzy at the bottom. We have learned to harness the chaos. We have built our civilization on top of a foundation that, quite frankly, makes no logical sense. To truly understand how mind-blowing this is, let us look at the most famous experiment in the history of physics, known as the double-slit experiment. Imagine you have a wall with two vertical slits cut into it, and you are throwing tennis balls at it. Some balls will go through the left slit, and some will go through the right slit. On the wall behind them, you would expect to see two bands where the balls hit. That is perfectly normal. But when scientists fired tiny electrons at two slits, something impossible happened. Instead of two bands, they saw an interference pattern, which is a series of many alternating stripes. This is the kind of pattern you get when waves of water crash into each other, not solid objects. It meant that a single electron was leaving the source, becoming a wave of possibility, going through the left slit, the right slit, and both slits all at the same time, and then interfering with itself. But here is the part that will keep you up at night. When the scientists put a sensor next to the slits to simply watch which hole the electron went through, the electron stopped acting like a wave. It suddenly went back to behaving like a solid little marble and created the normal two bands on the back wall. Just the act of observing it changed how reality behaved. It suggests that the universe knows when you are watching, and it changes its disguise accordingly. So the next time you lose your keys, maybe you did not simply miss them. Maybe the universe just hadn't decided where to put them yet. Copenhagen Interpretation. Imagine you are running late for work on a busy Monday morning. You grab your coffee, check your phone, and then you reach for your keys. They are gone. You check the kitchen counter where you always leave them. Nothing. You check your pockets. Nothing. You swear you left them on the table by the door, but the table is empty. You start tearing the house apart, looking under sofa cushions and inside drawers. Then, 10 minutes later, you look at that same table by the door again. And there they are, right where you looked the first time. It feels like the universe is playing a prank on you, does it not? It feels like the keys were not actually there until you decided to look really, really hard. Well, what if I told you that in the weirdest corners of science, that is actually how the universe works? We move through our daily lives assuming that the world is solid, fixed, and definite. If you leave a book on your nightstand and leave the room, you are 100% sure the book is still there. You do not need to stand there staring at it to keep it in existence. We believe that objects have specific properties, like position and speed, regardless of whether anyone is watching them. It feels like common sense. Reality is reality, and we are just observers passing through it. We assume that the tree falling in the forest makes a sound, whether we are there to hear it or not. But physicists in the early 20th century started looking at the tiniest building blocks of the universe, atoms and electrons, and they realized that our common sense might be completely wrong. They found that the rules of the game change entirely when things get really small. This brings us to one of the most famous and mind-bending ideas in history, known as the Copenhagen Interpretation. Developed largely by the physicists Niels Bohr and Werner Heisenberg in the 1920s, this theory suggests that particles do not have definite states until they are measured. Before you look at a particle, it is not in one specific place. Instead, it exists in a blurry cloud of all possible places at once. Physicists call this a superposition. To visualize this, imagine a spinning coin. Is it heads or tails? While it is spinning, it is kind of both, is it not? It is a blur. It only becomes heads or tails when you slap your hand down on it to stop it. The Copenhagen Interpretation says the entire subatomic world is like that spinning coin. Nothing is definite until an observer steps in and forces nature to make a choice. This idea shakes the very foundation of how we understand existence. It implies that the act of observation is not just passive watching, it is an active part of creation. When you measure an electron, you are not just finding out where it is. You are forcing it to take a stand. Before you looked, it was everywhere and nowhere simultaneously. By looking, you collapsed all those possibilities into a single reality. It makes us wonder about the nature of the universe itself. Albert Einstein was actually deeply bothered by this. He famously asked if the moon only exists when we look at it. He wanted a universe that followed strict rules, but the Copenhagen Interpretation suggests that reality is not a hard, fixed stage, but rather a fluid performance that reacts to the audience. To show just how absurd this sounds, another physicist named Erwin Schrödinger came up with a famous thought experiment involving a cat. Imagine you place a cat inside a sealed steel box. Inside the box, there is a tiny amount of radioactive material, a Geiger counter, a hammer, and a vial of poison. If the radioactive atom decays, the counter detects it, drops the hammer, breaks the vial, and sadly, the cat passes away. If the atom does not decay, the cat lives. According to the Copenhagen Interpretation, until you open the box to check, the atom has both decayed and not decayed at the same time. This means the cat is both alive and dead simultaneously. It is only when you open the box that nature snaps into one state or the other. Schrödinger actually created this example to show how silly the theory sounded. But today, it remains the best illustration of how strange quantum mechanics truly is. It reminds us that the universe is far more mysterious and perhaps more participative than we ever dared to imagine. String theory. Imagine you are sitting at a messy desk, trying to untangle a pair of wired headphones that have been sitting in your pocket. You pull at one loop, and it tightens another knot. You try to weave the jack through a gap, but it just creates a bigger mess. It is frustrating, right? We have all been there. Now, imagine if you could zoom in on that headphone wire. You would see the plastic coating. Zoom in closer, and you see the molecules of the plastic. Zoom in even more, and you see atoms with electrons whizzing around a nucleus. We are used to thinking that if you keep zooming in, you will eventually hit a tiny, solid dot that cannot be cut any smaller. We usually picture the fundamental building blocks of the universe as tiny, hard specks, like microscopic marbles or Lego bricks. This brings us to a common way we look at the world. We tend to crave certainty and solidity. In school, most of us were taught the particle model of physics. It is comfortable and easy to visualize. You have a proton here and an electron there, and they interact like billiard balls on a pool table. It makes us feel like the universe is made of dependable, concrete stuff. However, this mindset creates a massive problem for physicists. When they try to use the math of these tiny billiard balls to explain gravity, the equations completely fall apart. It is as if the rules for the big stuff, like planets and stars, refuse to play nice with the rules for the small stuff, like atoms. They just do not fit together. This is where string theory comes in to offer a radical new perspective. Imagine that we get rid of the idea of these tiny, hard dots entirely. Instead, string theory suggests that if you could zoom in far beyond the atom, deeper than the electrons and quarks, you would not find a solid particle at all. Instead, you would find a tiny, vibrating filament of energy. It looks like a little string. Some of them are open strands, like a loose thread, and some are closed loops, like a rubber band. The central idea is incredibly simple yet mind-blowing. Everything in the universe is made of the exact same type of string. The only difference between one particle and another is how that string is wiggling. This matters because it fundamentally changes our understanding of reality and could solve the biggest headache in science. Right now, physics is split in two. We have general relativity for heavy things like gravity and quantum mechanics for tiny things. String theory is the bridge that tries to unite them into a single theory of everything. Think about how this applies to the world around you. Everything you touch, the light from the sun, and even gravity itself, might just be different vibration patterns of these strings. But here is the catch. For the math of string theory to work, our universe cannot just have the 3 dimensions we see, which are height, width, and depth, plus time. The theory predicts there could be 10 or 11 dimensions in total. The reason we do not see them is that they are curled up so tightly that we can never experience them, much like a garden hose looks like a 1-dimensional line from far away, but is actually a 3-dimensional tube when you get close. To really visualize this, let us look at a famous analogy often used by physicists like Michio Kaku. Think of a grand guitar. If you pluck a guitar string one way, it vibrates to create an A note. If you pluck it slightly differently, it creates a C note. The string is the same material, but the vibration creates a different sound. String theory says the universe is exactly like this. An electron is just a string vibrating in the key of electron. A quark is a string vibrating in the key of quark. In this beautiful picture, physics is the harmony of these strings, and chemistry is the melody they play when they interact. Instead of a chaotic mess of particles crashing into each other, the universe becomes a cosmic symphony, resonating through 11 dimensions. It turns the hard, cold science of matter into something that resembles music. Superstring theory. Imagine you are holding a hot cup of coffee in your hands. You can feel the warmth radiating against your palms and the smooth ceramic of the mug. It feels solid, heavy, and undeniably real. If you were to drop it, gravity would pull it to the floor, and it would likely shatter. We move through our lives interacting with these solid objects, trusting that the physical world is made of distinct, hard stuff. We see a chair, a table, or a person, and we assume that if we just kept zooming in with a microscope, we would eventually hit the bedrock of reality. We assume we would find tiny, solid marbles that stack together to build everything we see. But what if that assumption is completely wrong? What if the solid ground beneath your feet is not actually made of hard particles at all, but rather of tiny, vibrating strands of energy? This is the mind-bending proposition of superstring theory. Most people view physics as a strict rule book where everything fits together perfectly. We learn about gravity in school, and we learn about atoms, and we figure the scientists have it all worked out. However, there is a dirty little secret in the world of physics. For the last century, our understanding of the universe has been divided into two warring camps that refuse to speak to each other. On one side, you have general relativity, which was Einstein's masterpiece. This explains the big stuff like stars, black holes, and gravity. On the other side, you have quantum mechanics, which explains the weird and chaotic world of the tiny, like atoms and electrons. The problem is that these two theories mathematically hate each other. If you try to combine the math of the big, heavy gravity world with the math of the tiny quantum world, the equations break down completely. They produce answers that make no sense, like infinity. It is like trying to load a video game cartridge into a toaster. They are fundamentally incompatible. This is where superstring theory enters the stage to save the day. It offers a beautiful and elegant way to unite these two fighting theories into one single description of reality, often called the theory of everything. Here is the core idea. Conventional physics says that the smallest building blocks of nature, like electrons and quarks, are zero-dimensional points. Think of them as tiny dots with no size. String theory suggests that if we had a magnifying glass powerful enough to see deep inside these particles, we would not see dots. Instead, we would see tiny, vibrating filaments that look like strings. These strings are incredibly small. To give you a sense of scale, if an atom were magnified to the size of the entire solar system, a single string would only be the size of a tree on Earth. But the real magic lies in how they behave. Just like a guitar string can play a different musical note, depending on how you pluck it or how fast it vibrates, these cosmic strings can vibrate at different frequencies. If a string vibrates one way, it appears to us as an electron. If it vibrates another way, it appears as a photon of light. If it vibrates a third way, it becomes a graviton, which is a particle that carries gravity. Suddenly, gravity is not an outsider anymore. It is just another tune played by the same string. One of the most famous ways to visualize this comes from the physicist Brian Greene, who compares the universe to a grand cosmic symphony. Before string theory, we looked at the universe as a collection of disjointed matter. But this theory suggests that everything, from the light of the sun to the DNA in your body, is born from the music of these vibrating strings. However, this musical harmony comes with a strange requirement. For the math of string theory to work, our universe cannot just have the 3 dimensions of height, width, and depth that we experience every day. The theory demands that there must be extra dimensions, perhaps 10 or even 11 total dimensions, that are curled up so tightly we cannot see them. Think of looking at a garden hose from far away. It looks like a one-dimensional line. But if you were an ant walking on the surface of that hose, you would realize there is a second dimension wrapping around the tube that the distant observer cannot see. String theory argues that these extra dimensions are woven into the fabric of space all around us, determining how the strings vibrate, and consequently, how our universe is built. While we have not proven it experimentally yet, superstring theory remains one of the most compelling ideas in human history, because it suggests that deep down, the universe is not a collection of hard, cold rocks, but a world of pure music and vibration. Loop quantum gravity, LQG. Imagine you're sitting on your couch watching your favorite movie in ultra-high definition. The picture looks incredibly clear and smooth. The colors blend perfectly into one another, and the movement feels seamless. But now imagine you stand up and walk right up to the television screen until your nose is almost touching the glass. Suddenly that perfect image breaks apart. You no longer see a smooth picture. Instead, you see thousands of tiny little squares called pixels. The image that looked continuous from far away is actually made of discrete little chunks when you get close enough. This experience of seeing the hidden structure behind a smooth image is the perfect way to understand one of the most fascinating ideas in modern physics. Most of us go through life thinking of space as an empty backdrop. We imagine it is like a smooth, silent stage where the drama of the universe plays out. We assume that if you took a piece of space and cut it in half, and then cut that half in half, and kept going, you could do that forever. We instinctively believe that space is smooth and continuous, like water flowing in a river. This view of the world feels natural to us because in our daily lives, we never see the pixels of reality. We assume space is just the container for everything else, and that it has no texture of its own. This assumption works fine for driving a car or catching a ball. But when physicists try to understand the deepest laws of the universe, this smooth view of space causes massive problems. It creates mathematical errors where the laws of gravity crash into the laws of quantum mechanics. This is where loop quantum gravity comes in to save the day. This theory proposes a radical shift in how we view the fabric of reality. Loop quantum gravity suggests that space is not smooth at all. Instead, it is made of tiny, distinct loops woven together. Think of it like a chainmail shirt worn by a medieval knight. From a distance, the shirt looks like a shiny sheet of metal. But up close, it is made of thousands of interlocking rings. In this theory, space is made of finite loops of gravitational fields. These loops are incredibly small. They are so small that if you zoomed in on a grain of sand until it was the size of the observable universe, these loops would still be tiny. The key takeaway here is that space is not a background. Space is a physical thing made of individual parts. You cannot divide space forever, because eventually you hit the smallest possible unit of space. This concept matters because it completely changes how we understand the most extreme objects in our universe, like black holes. In the old view of smooth space, a dying star collapses down into a single point of infinite density. This is called a singularity, and it is a mathematical nightmare because the laws of physics break down completely. But if loop quantum gravity is true, then a star cannot collapse into a single point because space itself has a minimum size. It is like trying to pour a bucket of water through a screen door. The water can only get so small before it is stopped by the mesh. This means that inside a black hole, matter might not be crushed into nothingness, but instead it might be packed into a super-dense ball of quantum loops waiting to be released. To see this theory in action, we can look at the biggest event in history, which is the Big Bang. The standard story tells us the universe began from a singularity, a point of infinite heat and density appearing out of nowhere. But loop quantum gravity offers a different and more dramatic story, often called the Big Bounce. Imagine a diver jumping on a trampoline. As they fall, the trampoline stretches down. It stretches and stretches until it hits its limit. The fabric cannot stretch any further, so it snaps back, pushing the diver upward. Loop quantum gravity suggests our universe acts the same way. It proposes that perhaps there was a universe before ours that collapsed inward. It squeezed down until it hit the quantum limit of space and then bounced back outward in a massive explosion that we call the Big Bang. This implies our universe might be just one breath in an eternal cycle of collapsing and expanding. It turns the cosmos from a one-time event into a living, breathing entity. Euclidean quantum gravity. Have you ever had one of those mornings where you are running hopelessly late? You are scrambling to find your keys, staring at the clock, and watching the minutes melt away. In that stressful moment, you probably wished you could just step sideways out of time. Imagine if, instead of time rushing forward like a wild river, it was just another direction you could walk, like turning left or right. It sounds like something from a science fiction movie or a dream. But what if I told you that the universe might actually have a mode where time behaves exactly like that? This isn't magic. It is a mind-bending concept in physics that tries to solve the mystery of how everything began. Most of us live our lives obsessed with the relentless ticking of the clock. We view time as a straight arrow that only flies in one direction. The past is a memory we cannot touch, and the future is a destination we have not reached yet. This linear view of time makes sense to us because it matches our daily experience. We get older, not younger. Cups break. They do not unbreak. Because of this, when we think about the origin of the universe, we imagine a starting gun. We picture a sharp, dramatic moment called the Big Bang, where the clock suddenly started ticking from zero. But this idea of a sharp beginning creates a massive headache for physicists. When they try to use math to describe that very first split second, their equations break down. It is like trying to divide a number by 0 on your calculator. You just get an error message. The laws of physics as we know them simply stop working. This is where a fascinating theory called Euclidean quantum gravity comes into play to save the day. It sounds intimidating, but the core idea is actually quite beautiful. To understand it, you have to remember high school geometry. Euclidean geometry is the study of flat spaces, like drawing triangles and squares on a smooth sheet of paper. In the messy world of Einstein and relativity, space and time are usually curved and warped. But in Euclidean quantum gravity, physicists use a mathematical tool called imaginary time to smooth everything out. Do not let the name fool you. Imaginary time is not make-believe. It is a real mathematical concept that transforms time so that it behaves exactly like a dimension of space. Instead of time being a ticking clock, it becomes a landscape. Why does this matter to anyone who is not a physicist? Because it completely changes the story of our origins. If you treat time as a spatial dimension, the sharp, jagged edge of the Big Bang disappears. Think about the planet Earth. If you start walking south, eventually you will reach the South Pole. When you get to the South Pole, there is no edge of the world. You do not fall off into nothingness. The point is just smooth and rounded. You simply cannot go any more south. Euclidean quantum gravity suggests that the beginning of the universe was exactly like the South Pole. There was no scary singularity or point of destruction. There was just a smooth, rounded bottom where space and time were blended together. This incredible idea was most famously championed by the brilliant Stephen Hawking and his colleague James Hartle. They called it the no-boundary proposal. To explain it, Hawking often asked people to imagine a shuttlecock, the kind you use in badminton. It has a rounded cork bottom. Hawking suggested that the universe is shaped like that shuttlecock in 4 dimensions. In the realm of real time, the universe expands like the feathers of the shuttlecock. But if you go back to the beginning, down to the cork, you enter the realm of imaginary time. There is no sharp starting point, just a smooth curve. This theory implies that the universe is completely self-contained. It did not need an outside clockmaker to start it. It just is. It suggests that if we could look at the universe through the lens of this theory, we would see that time is not a cruel master pushing us forward, but rather part of a beautiful, finite, and boundless shape that holds our entire existence. GISR, Gravity-Induced Spontaneous Radiation, Mechanism. Imagine for a moment that you are sitting in a perfectly still, dark room. It is so quiet you can hear your own heartbeat. You are holding a glass of water, and because you are sitting still, the water is perfectly flat and calm. Now imagine that without you moving a muscle, the water suddenly starts to ripple. Tiny waves appear out of nowhere, and maybe a drop even splashes over the edge. You would probably think you were hallucinating, or that a ghost just walked by. We expect things to stay calm unless something touches them or shakes them. We think of the empty space around us as a passive stage where nothing happens unless we make it happen. But in the strange world of advanced physics, empty space and the force of gravity are not just passive backgrounds. They are active, chaotic players that can make calm water splash without anyone touching it. This leads us to one of the most mind-bending concepts in theoretical physics, known as the gravity-induced spontaneous radiation mechanism. To understand why this is so weird, we have to look at how we normally think about the universe. Most of us go through life viewing gravity as a simple anchor. It is the thing that keeps our feet on the ground and keeps the Earth spinning around the sun. We tend to think of gravity as a constant, silent force that just pulls things together. On the other hand, we have light and radiation, which we think of as energy that comes from hot things like light bulbs, the sun, or nuclear reactions. In our minds, these are 2 totally different worlds. Gravity holds heavy stuff down, and radiation is energy flying around. We do not usually expect gravity to create light just by pulling on something. We assume that if an atom is sitting quietly in space, it will stay quiet unless it gets hit by something else. But this assumption overlooks a fundamental rule of the universe, which is that gravity can actually shake the quantum world until it breaks. This is where the concept of gravity-induced spontaneous radiation comes in. Let us break it down into simple terms. Everything in the universe, including the atoms that make up your body, has energy levels. Think of an atom like a person standing on a staircase. If the person is standing on a high step, they have a lot of potential energy. If they jump down to a lower step, they release that energy. In the world of atoms, when an electron jumps down a step, it releases a tiny packet of light called a photon. This is called spontaneous emission, and it is how things like neon lights and glow-in-the-dark stickers work. Usually this happens because of electricity or chemical reactions. However, the theory of gravity-induced spontaneous radiation suggests that gravity itself can push the person down the stairs. It proposes that if a particle is in a strong enough gravitational field, the warping of space and time acts like a nudge. Gravity squeezes the particle, forcing it to drop to a lower energy state and spit out a photon. Why does this matter? It matters because it blurs the line between matter and empty space. If this mechanism is real, it means that gravity is not just a silent container for the universe. It means that gravity is an engine that can turn potential energy into real, glowing light. It implies that in regions of extreme gravity, like near a black hole or a neutron star, matter cannot stay quiet. The gravity is so intense that it literally squeezes light out of atoms. This solves a major puzzle for physicists who are trying to connect the laws of the very big, like stars and galaxies, with the laws of the very small, like atoms and electrons. It suggests that gravity talks to quantum particles and can force them to reveal their energy. To visualize this, consider the famous equivalence principle introduced by Albert Einstein. He said that gravity feels exactly the same as acceleration. Imagine you are in an elevator in deep space where there is no gravity. If the elevator suddenly shoots upward very fast, you feel pushed into the floor. That feels exactly like gravity. Now, scientists have calculated that if you accelerate through a vacuum fast enough, you would actually see a glow. The empty space would seem to heat up and radiate light just because you're moving through it so violently. This is a close cousin to gravity-induced spontaneous radiation. It shows us that motion and gravity can shake the vacuum of space until it sparks. So the next time you drop a pen and watch it fall, remember that gravity is doing more than just pulling it down. In the deepest, most intense corners of the cosmos, that same force is squeezing the universe hard enough to make it glow in the dark. The Panspermia Theory. Have you ever opened your refrigerator to find a container of leftovers that you completely forgot about for 3 weeks? You carefully crack open the lid, and inside you see a fuzzy green forest of mold growing on what used to be pasta. You definitely did not put that green fuzz there. You did not plant it, and you certainly did not water it. Yet somehow, life found a way to show up, settle in, and thrive in that cold and dark plastic container. It feels like magic, but we know it is just biology doing its thing. Now I want you to take that image of the fuzzy leftovers and scale it up. Imagine that the refrigerator is the vast darkness of space, and the plastic container is our planet Earth. We usually assume that the mold, or in this case, human life and all nature, started right here inside the container. But what if the seeds for that life came from somewhere else entirely? What if we are just the mold growing on a sandwich that drifted in from a different cosmic neighborhood? This brings us to a mindset that most of us hold without even realizing it. We tend to think of Earth as a closed system, a lonely island in the universe, where the miracle of life sparked spontaneously from non-living matter. We look at our oceans and our atmosphere and think that the recipe for life was written, mixed, and baked right here on this rock. It is a comforting thought because it makes Earth feel special and unique. It makes us feel like the masters of our own home. Because of this, when we look for aliens, we look far away. assuming they are distinct and separate from us. We rarely stop to consider that the separation between us and the rest of the universe might be an illusion. We struggle to accept that we might be the intruders, or at least the descendants of intruders. This creates the perfect opening to talk about one of the most mind-bending ideas in physics and biology, called the Panspermia Theory. The word might sound a bit complicated, but it comes from Greek words that simply translate to seeds everywhere. The core idea is incredibly simple, yet revolutionary. Panspermia suggests that life does not necessarily begin on the planet where it ends up. Instead, life exists throughout the universe, distributed by space dust, meteoroids, asteroids, comets, and planetoids. Think of these space rocks as cosmic taxis or interstellar mail trucks. The theory proposes that microscopic life forms, like bacteria or extremophiles, can survive the harsh effects of space. They become trapped in debris that gets ejected into space after a planetary collision, and then they go into a deep hibernation. These sleeping seeds travel for millions or even billions of years until they crash land on a hospitable planet like Earth. Once they arrive, they wake up, multiply, and eventually evolve into everything we see today. The implications of this are absolutely massive. If this theory holds true, it changes our entire identity. It means that the distinction between us and aliens is blurry. In a way, we would be the aliens. It implies that life is not a miraculous accident that happens once in a blue moon, but rather a common chain reaction that spreads from star system to star system. It solves the massive scientific headache of trying to figure out how complex life formed on Earth so quickly after the planet cooled down. Instead of starting from scratch, Earth might have just provided the fertile soil for seeds that were already billions of years old. This connects us to the cosmos in a physical way. We are not just looking up at the stars. We might be made of biological material that was cooked up near them. To see why this is taken seriously, we have to look at a famous event that happened in 1969. A massive meteorite fell near Murchison, Australia. When scientists analyzed the Murchison meteorite, they were shocked by what they found inside. It was not just a dead rock. It was loaded with amino acids, which are the organic building blocks of life. These were complex organic compounds that formed in space, long before the rock ever touched our atmosphere. This proved that the ingredients for life can and do survive in the vacuum of space. While the meteorite did not carry little green men, it carried the chemical starter pack for biology. It showed us that the universe is not a sterile and empty place, but a messy kitchen full of ingredients flying around, just waiting for the right pot to land in. So the next time you look up at the night sky, remember that you might not be looking at a foreign place. You might just be looking at your ancestral home,